Hi, welcome to lesson 8.3, evaluating logarithms. So we've looked at logarithms over the past couple of lessons. The first one, 8.1, we kind of discovered that logarithms are used to evaluate exponents, where last year in grade 11, we were just to do some estimating to determine the value of an exponent. Now we have a tool to do so, and that's logarithm. 8.2, we looked at logarithmic graphs and their transformations, and they follow the same transformations as all other functions that we've looked at in the past. Today, we're going to be doing some evaluating. So just to recall here, we've got the exponential form of a logarithm here. And we also have then the logarithmic form in this case. And those are both inverses of exponential functions. We see that in the exponential form that y is the exponent. And we notice that the y is here in the logarithmic form. And so if y is the exponent in the exponential form, then obviously it is the same exponent in the logarithmic form, which then means that the logarithm itself is the exponent. Because if the logarithm of x to the base a equals y, and y is the exponent, that means that the logarithm is the exponent. So when you evaluate a logarithm, you're actually finding the exponent. And then further to that, we see that a is the base, and here we see a is the base for the logarithm. Okay. All right, so let's take a look here. Oh, and here's the graphs. The graph of when the base is greater than 1 looks like this. And when the base is a fraction, so greater than 1, any value that's greater than 1, of course. And if it's between 0 and 1, that means it's some sort of a fraction or decimal. So it's less than 1, but it's still positive. Okay, so these bases are always going to be positive. Greater than 0 is positive. And we see here that the graph of when the base is between 0 and 1 looks like this. Okay, so those are just two graphs to kind of keep in mind. Notice also, of course, that these graphs of logarithms do not come into the negatives. They always stay positive. So a logarithm cannot be negative. All right, so let's go down here and do a little bit of rewriting here, first of all. So we want to express these in logarithmic form. So here's equations in exponential form. We want to express them in logarithmic form. So first thing I like to do is I like to recognize, okay, well, which is the base, where's the exponent, and where is the result, the value. So I would write the value here, personally. And because it's in a logarithmic form, a logarithm is an exponent. Okay, so I can't reiterate that enough. So it is an exponent. So if we have a logarithm of some value, that is equal to the exponent. So the exponent is -3, so the exponent is over here, and the base is down here. Okay, please make sure that you write that base of 5 in this particular case as a subscript to the log. Please don't write it like that, because that's not where the base should go. The base should be down lower, okay, as a base would be. Okay. Okay, and that is that's logarithmic form for this expression here. Okay, so these things mean the same, but this is the logarithmic form of that. We'll write the logarithmic form of 8 to the power 0 equals 1. So we know that the result is 1. We know the exponent is 0. And it's a logarithm of base 8. So the logarithm of 1 to the base 8 is 0. Yeah, that's kind of how you would read that. Logarithm of 1 to the base 8 is 0, which means what do you raise 8 to result in 1? Okay, or get a value of. Okay, what do I raise 8 to the power of to get 1? And that case, in this case, is 0. Next one, I've got the result here, which is root 7. The exponent is 1/2. The base is 7. So I've got the logarithm of root 7 to the base of 7 is 1/2. So what do I raise 7 to result in root 7? Well, that would be 7 to the power 1/2. Or the answer to that question would be 1/2. Again, analyzing this next one. So we know we have a logarithm. We know the base. Okay, the base is 4. The result is the cube root of 4 squared. And the result is, the exponent then is 2/3. So what do I raise 4 to? What do I raise 4 to the power of to get the cube root of 4 squared? And that would be 2/3. Now we want to write it in the other direction. We want to express these in exponential form. Okay, so we just undo what we just did. So here's the result. I usually just write that right underneath there. We know the base is 7 and the exponent is 2. Okay, sometimes this one's a little bit more straightforward to envision. The result is 1/36. We see the base is 6 and the exponent is -2. Okay, because we know that the exponent is a logarithm. And here again, it's the cube root of 11 to the power 4 is the result. We see the base is 11 and the exponent is 4/3. Okay, so that's just expressing some of them. We're now going to get into some evaluating. So any time, I should have mentioned this before, but anytime along through the video, if you want to pause it and try it yourself, please go ahead and pause it before I go and ruin the anticipation for you. Evaluate each logarithm. When I do these, I always like to set it up into exponential form and then evaluate by getting common bases. So I'll usually set each of these equal to x. Now you don't have to do this, but this is how I'm going to show it. I set them equal to x, and then I write it in exponential form. And then from there, we can compare bases to make sure that we have the correct values. Okay, so the result is 16. We know the base is 2. The exponent is x. Well, so what I'll do now is I'll take a look at 16. Well, how do I write 16 as a power with base 2? Okay, well, I know the base is 2. And so 2 to the power, what gives me 16? Well, that ends up being 4. So this is telling us now that we have an equivalent. We've got equivalence. And we know that 2 to the power 4 is equal to 2 to the power x. Well, the other thing I notice is that the bases are the same. So if the bases are the same, and we have equivalence, the left side equals the right side, then the only option left is that the exponents have to be equal. Therefore, x equals 4. Therefore, the logarithm of 16 to the base of 2 is 4. Okay, to answer this question up here. All right, let's take another look here. 1 over 49 equals, well, x is the exponent because it's the logarithm. We got the base of 7, 7 to the power x. So I know I want the same base. So I read it as the same base, so there's a common base. So if I've got 1 over 49, well, I know that 7 squared is 49. So that means that the exponent probably has to be negative. So 7 to the power negative 2 gives me 1 over 49. We've got equivalence. We have the same base. Therefore, x has to equal negative 2. Therefore, up here, the logarithm of 1 over 49 to the base of 7 equals negative 2. Okay, then I guess you can, if you want, you can erase this x there. All right, take a look at this one. Maybe pause the video, see how well things are going. And so I know here I got root 5 as the result. The base is 5. The exponent is x. And so I've got the root of 5. How do I write the root of 5 as a power with base 5? Well, that would be 5 to the power 1/2. Okay, they're equal to each other. Both bases are the same. Therefore, the only option we have is that the exponents have to be equal. Therefore, x equals 1/2. Therefore, the logarithm of root 5 to the base 5 is 1/2. Moving on to D here. The result is 5 cubed. The base is 5. Exponent is x. Well, we've already got a common base. Therefore, x equals 3. We've got the 5th root of 3 all to the power 7. And that equals 3 to the power x. We know x is the exponent because it equals logarithm. We got a common base. We can rewrite this as 3 to the power 7 over 5. Okay, because we know that this is the root, and that's in the denominator of a rational exponent, and that's the power. Therefore, we've got 3 to the power 7 over 5. That equals 3 to the power x. Therefore, x has to equal 7 over 5. Same thing goes here. So we're going to now, this is interesting. So we got 4 to the power logarithm of 4 to the 64. So we're going to ask, well, what do I raise 4 to get to the power 64? And so recall that this whole thing, A, it's an exponent, and B, it's actually in the exponent. So it's actually the exponent we're looking for. And so if you were to say logarithm of 4 to the base, or sorry, 64 to the base 4, well, what do I raise 4 to get 64? Well, 4 squared is 16, and 16 times 4 would be 64. So that equals 3. So the logarithm of 64 to the base 4 is 3. Therefore, 4 cubed equals x. Therefore, x equals 64. So notice again that I made this whole thing equal to x. And I had to solve this left side to get the value of x. And I see that log of 64 to the base 4, this part here, the exponent, is 3. Therefore, 4 cubed is x. 4 cubed is 64. Therefore, x is 64, which means that 4 to the exponent log of 64 to the base 4 equals 64, which then tells me that this part, the 4 and the log of 4, basically cancel. I'm sure that's not the exact way that that should be displayed, but the result is that if you've got the same base here and here, then the result is just 64, or the result is the same. Okay, if we look over here in part G, same sort of idea now. We see we got a base of 9. We got a base at 9. Those are going to just basically cancel. And we're left now that x equals 81. If we examine the logarithm of 81 to the base 9, well, again, we say, well, what do we raise 9 to get 81? Well, the answer is 2. Therefore, this 2 will replace that, whatever's in brackets. And then we actually end up having 9 squared equals x. Therefore, x equals 81. Therefore, the 9 to the exponent log of 81 to the base 9 is just 81. Okay, so it ends up, because those bases are the same, we end up just getting the same value that we had right here. Okay, that ends up being the same thing. So in general, what we've found here is that what we just looked at in the last couple of examples, b to the exponent log of x to the base b is just x, and the logarithm of b to the power x to the base b, well, what do you raise b to get b to the power x? Well, that's just x. Okay, so notice that in each of these cases, we've got the same base for these. Therefore, the result is just this x. Okay, we want to evaluate the following by estimating. So now the change of base formula is given to you right here. I'm going to show you how that works by looking at this here. So again, I'll do the same thing. I'll set this equal to x. I'll then say, okay, here's the result. The base is 5. The exponent is x. Now, generally, the change of base formula isn't given until later. There's some other rules of logarithms that we have to look at, and we'll probably look at that in section 8.4. So if we're to estimate, well, then we're just going to basically be guessing values in here. So if x is 2, then the right side equals 25. If x is 3, then the right side is 125. So we know it has to be between 2 and 3. Then you can start guessing. We know that 50 is closer to 25 than it is 125. So maybe you can say x could be 2.3, for example. Okay, and then you'd have to do that calculation. And unfortunately, I don't have my calculator with me to figure this out. What you're going to find in, well, probably next lesson, is that when we have an exponential form like this, what you can do is you can take the logarithm of both sides. So I'm just going to, it's just like anything else where we have, you add something to both sides, you divide both sides by the same number, you take the square root on both sides. We're just taking the logarithm of both sides. Now, one of the rules of logarithms is that what we can do is we can take this exponent here, and we can actually move it down in front. Okay, so then we get x logarithm of 5. And then what we can do, because that's multiplication here, we can just divide both sides by the logarithm of 5. Therefore, if you're trying to figure out the value of x is the logarithm of 50 divided by the logarithm of 5. Okay, notice that whatever's on the bottom here, whatever the base is on the bottom here, and whatever's the larger value up here is in the numerator. Okay, and that is the change of base formula. Okay, and then with this, they call it change of base formula because we can use it whatever base we want. In this case, we notice that because the base is not written, that the base is 10 in both cases, of course. But we could write that any way we want. We could write that as the logarithm of 50 to the base 4, if we wish, as long as the denominator also has the same base. And that's going to give us the same number. Okay, we could do the logarithm of base, I don't know, root 6, if we so desire. Doesn't matter as long as the bases are the same. That will give us the same value. Okay, that's why they call it the change of base, because you can use this to now change the base to what's most convenient for you. Okay, and then from there, again, I don't have a calculator handy with me, but you can just take the logarithm of 50 divided by logarithm of 5. You can do that on your calculator because your calculator works in base 10, and you can just do that division. But make sure that you do the logarithm of 50 and get that value, then divide by the logarithm of 5. If you want to put it in your calculator all at once, you may want to consider using brackets just to make sure it's all sticks together. But you have to take the logarithm twice, once for 50 and once for 5, and then divide those results. And then we move down here, solving exponential equations. Sometimes we have something, a real life issue, like radioactive materials. We usually use those in examples as half-life. So this is the formula. This is the mass remaining. The mass remaining is on the left. The initial mass is that value. The half-life is 1,620 years. So that actually is the H. The factor we use to represent half-life is the 1/2. Okay, but the half-life itself is this value of h. And this formula, when you have t over h, that's telling us the number of half-lives. Okay, that's why we have to divide. We're grouping them in terms of half-lives. So if t is 1,620 years, for example, then t over h is then just 1 half-life. If t were 3240, for example, then t over h, that exponent, is 2 half-lives. Okay, so we're finding the half-life, or the amount of time for, or we're looking at the result, the remaining amount after 2 lives have passed. So in 1 half-life of 1,620 years, some original sample decays to half its original size. It's going to take then 1,620 years for that half to decay to half of its size. So if we start with 5 grams, after 1,620 years, it decays to half of its size. After another 1,620 years, it decays to half of that. Okay, and then after another 1,620 years, it decays to half of that, which is, what's that, 0.6, am I right, 25, something like that. So we see that it slows down. So as it actually, the graph actually is more like that. It's like exponential. So the longer time goes, the less quickly the material decays. So it took 1,620 years to decay from 10 grams as well. So it decayed 5 grams in 1,620 years. Then a few half-lives later, it's taking 1,620 years to decay 0.625 grams. Okay, so that's, so it slows down over time. Anyway, so the reason why we have this exponent is we're grouping this calculation in terms of groups of half-lives. Okay, so getting back to the problem here, we're starting with 5 grams. It ends with 3 grams. We know it's a half-life, so we're using 1/2 as the decay factor. We don't know how long this is going to take, but we do know the half-life is 1,620 years. Okay, so we just have to dismantle this. So first of all, we can't really touch that exponent until later, so we're going to divide both sides by 5. And it's 1/2 to the exponent t over 1,620. Now, again, we don't know the rules for logarithms yet, but we will. So I'll just give you a little foreshadowing here. So we're going to take the logarithm of both sides. Actually, I'll do this up here. And because we've taken the logarithm, we can now bring that exponent down in front. So I've got the logarithm of 3 over 5 equals t over 1620, the logarithm of 1/2. Okay, this is multiplication. So then what I can do is I can divide both sides by the logarithm of 1/2. Again, when you do this calculation, you have to take the logarithm of 3 over 5, divide by the logarithm of a half, and get your answer there. And now we've got on the right t divided by 1,620. And because that's division, we can multiply both sides by 1,620. To form that 1. And we can get rid of this and that. And now that leaves us with t. So your time is 1,620 multiplied by the logarithm of 3/5 divided by the logarithm of a half. Okay, and that's how long it's going to take an initial sample of 5 grams to decay to a final amount of 3 grams. Okay, and that is how that is done. So here's a little bit of work for you to devour, and we will review any solutions that you would like to take a look at when we get back to class together. So thanks for watching, and we'll see you in class.